Okay, it's going to have straight sides. Well, what has to be true about those sides if it's considered regular? Right? They're all congruent. Exactly right. So if it's a regular polygon, it means that every single side is the same length. If you don't have this concept in today's assignment, it would be really, really hard to do. Okay? So you want the directions to say that every single problem is a regular polygon. And that's what we're going to concentrate on. So there's going to be a new formula today. And you have to write the formula a specific way. But, as I said, I kind of figured out a new way of doing this. So, the first thing I want you to do is, I just want to make sure I get the same shape. I want you to try to draw a regular pentagon. Okay, so what's a regular pentagon mean? 5 sides. Okay, so try to draw a regular pentagon. That one's probably pretty bad. Looks like I should have had a little bit more. So what Lauren said is that all of these sides should be congruent. Now obviously you can probably tell that mine aren't. This one is way shorter than the other ones. But we're going to try to find the area of regular polygons. Now, if I told you I wanted to inscribe this polygon in a circle, where would I do the circle? I'm going to put the circle on the outside. So this is the part where you want to try to draw your circle, and the circle hits every single vertex of whatever shape that you're drawing. In our case, it's a pentagon. Mine's not a very good circle. Okay? So if you notice up on the board here, this is, computer generated, so it's kind of a perfect one. And so it really helps if you can get this. But realistically now, if I hit this right here every single time, and I then found the center of my circle, would you agree that I could draw a radius, and I could draw a radius to every single point on my whatever figure it is, in our case, pentagon? So if I drew this segment right there, or I drew this segment right here, and I can keep going around, there's going to be obviously way more radii in this, but each of those radii touches an exact vertex of whatever shapes on the inside. Would you agree with that? So this is a special one, but each one of these is a radius because it goes from the center and touches the outside of the circle, but it also goes from the center and touches each vertex. Okay, so each one of those is a radius, but I'm going to erase, so I'm just looking at basically one triangle. Now, if I looked at this angle right here with respect to the circle, what kind of angle would I have in that problem? It's a central angle, right? So what did we know about the central angle and this arc? They were the same thing, right? But if it's a central angle, would you agree that I can then have that same angle all the way around in my pentagon? Right? So could I figure out what this angle is right there? How could I figure out what that degree measure is right there? If it's a regular pentagon, how many of these triangles or these angles would I have if I went all the way around? I'd have 5 of them, right? So how could I figure out what that specific angle would be? I'm going to take 360 divided by, I'm going to say n for right now, because n is just going to be the number of sides of my polygon. So I'm going to use that. But in our, like you said, it would be, in our case, 360 divided by 5. So what's that middle angle? What is this? Let me know. 72, right? Mental math. You get that? Okay? So, again, what am I going to use this for? I'm going to use this to find the central angle for regular polygons. Would this work if this wasn't a regular polygon? If this wasn't a perfect pentagon? Would that work? No. So that's where, if the directions don't say this, you're kind of in a little bit of trouble. It's going to be a lot harder to do. Okay? Are we okay with this concept? Because this is going to be really important. Now, realize, if you go through this process and keep doing it over and over again, you're going to realize what a pentagon is, what a hexagon is, what an octagon is, and so on and so forth. And you won't even probably have to do this math. Now, if you have to do the math every single time, you have to do the math. But if you use it over and over again, it's not going to change because they're all going to be regular. Meaning they're all going to be the same, consistent. Okay? So this is the concept that we're going to try to look at today. Now, if I then went from this central angle, which we would know that right now this central angle is how much? 72 degrees. I'm going to put my little 72 in there. But if we go from this angle right here and draw what I would call a what right there? What would that be considered in my triangle? Okay, it's an angle bisector, but it's also an altitude. So I'm going to put a box there. And so, exactly like somebody said with the angle bisector, if I draw that altitude, this angle right here is going to be considered how much? I'm going to take whatever my central angle is and divide it by 2. So in our case, with a pentagon, we'd have 36 there. But when I draw this altitude, what else do I do to the bottom side of my angle? Or, sorry, the bottom side of my triangle? I would do what to this side right here? If this is truly, what kind of a triangle would I have made if this is a radius and this is a radius? It has to be an isosceles triangle. And so, if this is an isosceles triangle, that means this distance would have to be the same also. So when I draw this dashed line or my altitude, what would I do to that side? I'd split it in half, right? So realistically, I could come back and put a slash here and a slash here because I know that that's going to be true. But this line right here, which we call an altitude, in this particular case, it has a new name, and this is what we introduce as the apothem. So the apothem would be, if you wanted a straight definition, a segment drawn from the center to the side of a regular polygon forming a 90-degree angle. And realistically, we could think about this apothem as an altitude. So there's a couple different ways that now I can try to figure out this shape's area. All right? So we're going to try to find the area of any polygon. Sorry. It's got to be regular though. And we're going to do this in a couple different ways. So if I realistically went back and I replaced my radii that I erased Would you agree that all of those triangles that I just made would be the same thing? Right? Because each one of these has to be the exact same thing because all the radii would have to be the same measure. And if it's a regular polygon, like the lady said over here, each of my sides on the outside would have to be the same. So realistically, if I wanted to find the area of this whole thing, what could I do? Times however many triangles there were, right? Okay, so that's one way that I could do this. So to find the area of a polygon, I could find the area of one triangle and multiply by what? How can we say that? The number of sides or the number of triangles, right? Multiply by the number of sides. Because the number of sides tell you the number of triangles. So again, like I said, I don't know why it really dawned on me today that this is probably a way easier concept for you to think about. Because we have done the area of a triangle, right? What's the area of a triangle again? Base times height divided by 2. And do I have that in the things that I drew in this little figure? My height is really my apothem, and the base would actually be what? The outside of each side of my, whatever we're talking about. In our case, again, a pentagon. That makes sense? So we have our base times height, and all we do is divide by 2 because it's half of a rectangle, and then we're going to multiply it by the number of sides in whatever shape that we're talking about, because that's actually how many triangles that we have. So if you want to think of it that way, you can totally think of it that way. Basically, we're going to think of it as the same way, but we're going to say it in a different way. So if you look at this in the book, you're going to say the area of a regular polygon is going to be, and this is where you got to be careful with the letters again. We're going to say it's going to be 1/2 times capital P. What do you think capital P means? Yep. So this is going to be the perimeter of my regular pentagon, or a regular polygon, sorry, it could be a pentagon. So capital P times little a. What do you think little a stands for? What did we introduce today? The little a is my apothem. So if you want to kind of think about a new concept, you're going to use 1/2 P times A. If you're going to think about an old concept, you're going to think about taking the area of one of those triangles and just multiplying by the number of triangles. Essentially, though, you're going to do the exact same process because you're going to have to do a lot of math in order to find the pieces that you need. All right? So they're going to give me one of the pieces in the triangle or regular polygon, and then I have to use that to find the other pieces. And essentially, you can then put it into whatever formula that you want. So how do I find those pieces? I find those pieces by doing trigonometry. What's trigonometry again? That's my SOHCAHTOA, right? So if I can do trigonometry, then sometimes I can do what? Special right triangles. And maybe even Pythagorean theorem. So you're going to use any one of those to try to figure out the pieces that I actually need, or the parts of my regular polygon. Special right triangles, again, what do we remember? We kind of had this conversation the other day, that if you do special right triangles, some of you didn't like it, some of you did, but my two special right triangles are 30, 60, 90. or what? 45, 45, 90. And then you just have to know the ratios that go with those, right? It's 1, 2, square root of 3. And then 1, 1, square root of 2. So again, if you don't like the concept of special right triangles, you don't really understand it still, then you go back and use SOHCAHTOA. And again, sine, cosine, and tangent. And we'll show you how you're going to get to that point in this process in just a second. Okay? Questions here? So if you look at the actual book, they go through a process of actually helping you find how to get to this formula, but sometimes it just does more confusion than anything, so we kind of skip that part today. Okay? Now there's one more whole section or part of this assignment, but I want you to get this concept first. So we're going to go over examples of this first. Okay? So the first thing that we want to concentrate on is this. This right here is just asking you if you understand basically the new vocabulary that we introduced. So, in the figure, it's a pentagon. PQRST is inscribed in circle X. Identify the center, the radius, and apothem, and a central angle of the polygon. Then find the measure of a central angle. Now, realistically, they probably should have put one more word in there in those directions. They should have said that in the figure, it's a regular pentagon, PQRS. And that will enable us to get to all that stuff. So, what is a center of this circle? Or the center of this polygon? X, right? What's one radius? X cubed, right? What's another radius? XR. What's another radius that they didn't draw? X what? T. Exactly right. Everybody agree with that? Okay. So what's a central angle? What's the central angle that they drew in this picture? RX cubed. Exactly right. And what would the degree measure be of that central angle? 72 again. We already did it, right? Okay? So here's the thing. Think about this. What's the central angle of a hexagon? What would I do? 360 divided by 6, or I'd get 60 degrees, right? What's the central angle of an octagon? Come on, mental man. So now I'm doing 360 what? Divided by 8. 45. So if I do a pentagon, I get 72, and when I draw my altitude, I divide 72 in half, right? So I get 36. I still get a whole number. If I do my hexagon, you told me the central angle is how much? 60 degrees. And if I draw that altitude, I cut 60 degrees in half, so I get what? 30, and that's where I can use my special right triangle. Now, when I do this octagon, and I think there's one of those in the assignment, when I do the octagon, I have 45 degrees, but when I draw that altitude, I cut 45 degrees in half, and so then it gets a little bit more complicated because my angle is how much? 22.5. And so I just get decimals. So what I'm getting at is, it can happen over and over again. So when you see a pentagon from here on out, you'll automatically just think, well, the central angle in that has to be 72 degrees. And it doesn't matter how big the pentagon is. It could be a ginormous one, right? It could be one that's bigger than that wall. But the central angle, if it's a regular pentagon on that wall, still has to have a central angle of 72. Compared to this one right here that's really small. That makes sense what I'm saying? Because it's regular. If they don't say that it's a regular whatever, then it's really, really hard for us to do this. You got to do a lot of math. And some of you don't like to do simple math, let alone a lot. Okay? What else did we say? What's my apothem in this? XN. Remember, I can draw an apothem wherever I want. So I could have drawn it from X straight down, and then we would have just had to call it something else. Everybody okay with that? So you got to be able to understand what we have here. So now we got a what? A hexagon. Okay? So again, we already kind of said this. My central angle for a hexagon would be how much? Hexagon. 60 degrees, right? 360 divided by the number of sides, which is 6. Okay, what's my apothem again? GH. All right? So, all right, so here's the next thing. So basically now what they're trying to show you in this is the concept that we introduced right here. That if I can figure out the area of one of the triangles that's made in that, then I'm going to basically use this and I can bypass this formula right here. Then I don't have to think about that other formula. So in this right here, do I have enough information? Do I have a base and a height of that, of each little triangle? Yeah, what's my base? 3, and what's my height? So if I'm going to do this problem right here, I'm going to do base times height, which is 3 times 1.7, and what do I have to do to that? Divide by 2, and then to find the area of the whole thing, I would multiply that number by what? 6. Everybody agree with that? And so I get 15.3. Okay? Now, let's do this formula right here, even though that we don't have to. Do I have the apothem? Can I find the perimeter of that shape? Yeah, what's the perimeter? 18, right? So if I take 18 times my apothem, which is 1.7, and then divide by 2 or multiply by 1/2, I get 15.3, the exact same thing. So all I'm trying to prove to you is that these two formulas are the exact same thing. It's just how you see it in your mouth. Okay? Everybody get with that? All right, now we go on to what I would say that you can still pick which one you want to do, but now we're going to go through the whole process. So what don't we have in this problem that we had before? We don't have the apothem, right? So now, no matter what you're going to use as your formula to find, if I'm going to use the new formula 1/2 p times a, or if I'm going to use the old formula of finding the area of the triangle and then multiplying by the number of triangles, you still have to do the process of trying to find that apothem. So how the heck do I do it? That's the question. So, again now, when you draw this line down here, this apothem, my apothem is the pink dashed line. What does it do? It cuts what in half? It cuts the side in half. So this right here is how much? 2.5. But what else does it cut? The angle. So first off, we needed to know what was my central angle in the first place. 60, right? Because we're back to a hexagon, right? So I take 360 divided by 6, and I get 60 degrees. So when I draw that apothem, SPR turns into how much? That right there is how much? 30 degrees. Everybody understand why that is? Okay? Now, here's the question. Basically, what they're asking me to find, I'm going to use X because I don't want to draw an A. How do I find that X? I can do special right triangles. Special right triangles still, to me, are way faster than doing SOHCAHTOA. But if you didn't like it, you can still always use SOHCAHTOA and it's going to work. Now, here's the thing. So, if I'm going to do special right triangles, remember now, this side right here would have a ratio of what? 1. Perfect. This one would be what? 2. And this one would be the square root of 3. Awesome. That's a 3. Well, that's even worse. Okay. Anyway. So, what do I do to 2.5 to get it over here to the x? So my apothem, or x, is really what? 2.5 times the square root of 3. Now, do I have to simplify that? Not really. But notice here, if you're going to punch this into your calculator, and you put 2.5 times the square root of 3, you don't have to put square root of 3, you can just write it all together. 2.5 square root of 3. You hit equals, look at how big the, if you can see this, look how big the decimal is. You have to use that entire decimal in the problem when you're doing the math. Okay? Do not round until the very, very end of the problem. Okay? Now, realistically, I don't know if you can see this or if you did it on your own calculator, but it's 4.330. If you get a 0 in that long decimal, you can honestly stop right there. You can basically throw the rest of those out. Does that make sense? So when I'm telling you that you have to use, I would never really punch this into my calculator. I would just do the math, or have the calculator do the math, and just keep hitting the answer key or whatever. Okay? So, what am I going to do with that apothem? I have two choices. Okay? Did I need that apothem to do both of these? Yes. Because that apothem acts as my height in this triangle version anyway. Okay, so now you got to decide, which one do I want to do? Do I want to do 1/2 p times a, or do I want to do the area of the triangle and multiply by the number of triangles? What do you think? Area of the triangles. Okay, so Con wants to do one way, Merrick wants to do the other way. That's why I introduced both of them. I'm going to prove to you that it works both ways. So if we do Con's way, right, we're going to do 1/2 p times a. What's my perimeter, Con? 30, right? Here's the thing. When you go back to do the perimeter, yeah, we just emphasized that we cut this side in half, right? But when we come back to do the perimeter, we want the length of that whole side. So he has to go back to 5 and take 5 times 6. Everybody good with that? So Con's going to do 5 times 6, which is 30, and then he's going to take that times what? Whatever we got for that apothem, right? And then at the end, I'm going to divide by 2. So that's using this formula right here. Merrick wanted to do it the other way. What's Merrick going to do? He's going to do the base times the height. So what's your base and your height, Merrick?
The base is 5 and the height is 3.5.
Exactly right. So again, when you do this, go back to the 5, the whole length of that side. Don't do the half of that side. So Merrick's going to do our number times 5. What's he going to do to that number? Divide by 2, and then what's he going to do to that number? Multiply by 6, because why? Essentially, there's 6 triangles in that figure. So we get 64.95. Huh? 64.95, right? If you do it the way that it's up on the screen. So you're going to get it both ways. It's just what makes more sense to you. That's why we're showing you both ways. Okay? Does that make sense? All right. So this one to me is a little simpler because you really only have to do one thing. Because they gave you one of the 2 segments that you need. They gave you the length of the side of the polygon. So you didn't have to find both. In some of the problems, and we'll show you one of those, you have to find both. So you have to set up 2 different trigonometry problems. Or 2 trigonometry equations. And I believe that is this one. So, here's our question. I want you to, if you're taking notes or whatever, otherwise find a little piece of scratch paper. And I want you to tell me what this central angle is. And then I want you to cut that central angle in half and set up your trigonometry problems. So, Does everybody understand what I'm saying? What is this overall angle of C in this particular problem? How much is my central angle in a pentagon? 72. We already did that one, right? So when I draw that apothem, which is CD in this, what does that little angle C end up being? 36. Okay? So I'm helping you with that part right there. This angle right there is 36 degrees. Okay? Now I want you to set up, what do I need? I need this side, let's call this side X, and I also need my apothem, and we can call that A this time. So how do I find those two lowercase letters? What's the equation I would have to set up to find little a, and what's the equation I'd have to set up to find little x? This is where I can't go back and use special right triangles, right? Because I don't have one of those special angles. I have to use trigonometry in this one. So what relationship do I set up? So you're going to have two different problems. Now again, to me, this is the one that gets a little bit of a pain in the, you know what, because the decimal answers that you get are really long. And you have to use one of those long decimals in your answer. Or in your problem, sorry. I'm going to write the two equations over here. I don't want to rush you, but we're almost out of time, and I want you to at least see that if you did this right or wrong. So the first one that I would have done to find x is this formula. And the second one to find A, I'm going to do this. Did you agree with those two? Everybody did that? Now, how do I solve those? What am I doing with sine of 36 and x over 9? I'm just multiplying sine of 36 times 9. Okay? And so wasn't x a really long number? Or a long decimal? It did stop? Oh, it had a 0? Was that the one that had a 0? Okay? So what do you have to realistically do with that number though? I gotta multiply it by 2, right? Because when I figure out this x right here, I'm finding this little segment right here, and I have to double it because I want to find that whole length of that sine. Does that make sense? Now you might double it or have to divide by 2 if you're doing something like that, but you're right. Okay? So essentially, cons dividing by 2 and is the half. My multiplying by 2 is getting it back to, so they basically cancel each other out. If you understand what I just said there. Okay. Everybody good with just setting those up? Okay. So, here's the nice part, no math over the weekend. If you want to do